Chapter 8, Sections 3 and 4 are primarily concerned with eigenvalues and eigenvectors for symmetric matrices. So let's start out with letting A, first of all, be a square, real, symmetric matrix. So it equals its transpose. Then there exists a non-zero real eigenvector for A. Remember, in the previous section, the fundamental theorem of college algebra that tells us that roots always exist for polynomials, but in this case we find that this one must be real. Theorem 3.2, Part A. Let A be a real symmetric matrix. Then the eigenvalues of A are all real. That's important. A real symmetric matrix, all of the eigenvalues are real numbers. There are no complex eigenvalues. So that makes real symmetric matrices easier to work with. Only have to deal with irrational eigenvalues. So look at the proof of this statement. Start out with the definition of eigenvalue. Let AV equal lambda V. And so then we look at the scalar product. Okay? The scalar product of lambda V with V, which is equal then to the scalar product of AV with V, and commute that, turn it around, which is the same thing as V, scalar product V with AV, which is scalar product of V with lambda V. Now remember the fact that if you factor out a scalar on the second component, it would factor out with a complex conjugate, lambda bar. So you get lambda bar times the inner product of VV. Then if you subtract the two ends here and simplify, you find out that lambda minus lambda bar times the scalar product of VV is 0. But since we have a positive definite scalar product, which means that the product of V and V is always non-negative, must be the case that lambda minus lambda bar equals 0, which means that lambda is equal to its conjugate, which means that lambda is real. So here the idea is to prove that a scalar is a real number by showing that it's equal to its own conjugate, meaning the imaginary part is 0. Okay. Next we find, again, let's consider our vector space V over K with a non-degenerate scalar product, and let A be an operator on V, be a symmetric operator, symmetric. If lambda 1 and lambda 2 are distinct, different eigenvalues of A for the symmetric operator, okay, and remember there's the definition of symmetric in the brackets, then their corresponding eigenvectors, V1 and V2, are orthogonal or perpendicular. So here's the proof, and you're responsible for this. So let's start out by looking at it. All right, so we have lambda 1, and we're looking at the scalar product of the two eigenvectors, V1 and V2. Ultimately, we've got to conclude that the scalar product is 0. Alright, so let's multiply by lambda 1 and then put lambda 1 inside on the first component, and using the fact that it's an eigenvalue, we have equals the scalar product of AV1, V2, and since A is symmetric, we can move A to the second component. Remember, normally, if we move A to the second component, it would be the transpose of A. But since A is symmetric, the transpose of A equals A. So we have A. And then AV2 is lambda 2 V2. Then factor out the lambda 2. Subtract the ends. We see then that since lambda 1 and lambda 2 are not the same, that it must be the case that the inner product of V1 and V2 is 0. Hence, the eigenvectors must be perpendicular or orthogonal. Okay, so that's not hard to follow, hopefully. Now, next, let V be vector space over the real numbers with a positive definite scalar product, and let A be an operator, be a symmetric operator. Theorem 4.1 says, when we have V over R, positive definite scalar product, A being symmetric, then A has a non-zero real eigenvector. A non-zero real eigenvector. We saw a moment ago that they have a non-zero real eigenvalue. I have decided to skip over the material here on what it means for a subspace of V to be stable under A or invariant under A. So I've decided to skip that part. Okay. Go down next to section 8.4. Now in section 8.4 we have the spectral theorem. This is the main result in this section, the spectral theorem. The set of all eigenvalues corresponding to an operator A is called the spectrum of A. So starting here with the real case, V over R, finite dimension n, positive definite scalar product, with A being a linear operator, symmetric. Then the theorem says that the vector space V has an orthonormal basis of eigenvectors. Has an orthonormal basis of eigenvectors. And this will also imply that it can be diagonalized. Now, the proof is quite involved, but I do want to look at it. So, we know by a previous theorem that A has a non-zero eigenvector V not 0. So start out by letting W be the span of that single vector, one-dimensional subspace of V. And then we go through this process of W being stable under A, and eventually you have to extend and use induction, and you come out with an orthonormal basis of eigenvectors. Now, there is another handout that I uploaded in your content that tells you more about the next result. A matrix A is orthogonally diagonalizable, or OD for short, if and only if A is symmetric. Now, this is actually the one that you're responsible for. I misspoke a moment, not the other one, but this one. Okay, a matrix A, and this is known as the fundamental theorem for symmetric matrices. A symmetric matrix A is orthogonally diagonalizable if and only if A is symmetric. Now, first of all, let me note the definition of orthogonally diagonalizable. A square matrix is orthogonally diagonalizable if it is similar to a diagonal matrix through an orthogonal matrix. All right, so the proof in the forward direction, suppose A is orthogonally diagonalizable. That means that there exists a real unitary orthogonal matrix U with transpose UAU equal to the diagonal. Remember here, transpose of U is the inverse of U. Remember, for a unitary matrix, the inverse is equal to the transpose. So if you turn that around, that means that A is equal to UD transpose U, which implies, if you take the transpose on both sides of that equation, you find that the transpose of A equals UD transpose U, which is A. So what have we found? We have found the transpose of A equals A. That means that A is symmetric. It equals its own transpose. And in the converse direction, suppose A is symmetric. Then by the spectral theorem, which is theorem 4.3, Rn has an orthonormal basis of eigenvectors. Call them x1, x2 through xn. Let U be the matrix whose columns consist of these orthonormal eigenvectors, x1 through xn. Then U is a real unitary matrix, and U transpose AU equals the diagonal D, meaning that A is orthogonally diagonalizable. Now here's an example. Let's look at the 2 by 2. A equals negative 2, 2, 2, 1. So first find the characteristic polynomial P sub A. Take the determinant of Ti minus A and find the two eigenvalues. They're negative 3 and 2. And for each eigenvalue, we find the corresponding eigenspace. So for lambda 1 equals negative 3, we get an eigenspace of negative 2t comma t. So if we let t be 1, we get an eigenvector, a basis for the eigenspace, as negative 2 comma 1. And similarly, for lambda 2 equal 2, we wind up with a basis for the eigenspace, if we take t there to be 2, to be 1 comma 2. Now, those two vectors, x1, x2, those are the eigenvectors corresponding to the two different eigenvalues. And so we already know that they're linearly independent, and we also know that they are orthogonal. The only thing left to do is normalize the vectors. So thankfully, you don't have to go through the Gram-Schmidt process. All you have to do is divide the vectors by their norm. So if we divide x1 by the norm of x1, which is the square root of 5. We get negative 2 over square root 5 and 1 over square root 5. Divide x2 by its norm. We get 1 over square root 5 and 2 over square root 5. Now, let U be the unitary matrix whose columns consist of these two normalized vectors, U1 and U2. Then we find that the transpose of U times AU equals the diagonal matrix D, whose main diagonal entries are the eigenvalues negative 3 and 2. Now, next, we didn't really cover section 8.5 or section 8.6 particularly, but we need to look at some things contained therein. In section 8.5, we find the Hermitian case on page 225 of our book. So the Hermitian case. So if V is a vector space now over the complex field with a positive definite Hermitian product, let A be a linear operator, be a Hermitian operator. Remember, Hermitian means that it equals its adjoint, A star. And it turns out that all of the eigenvalues of A are real. And the proof here that I give, again, is not the same proof as in the book. I like my proof better. Again, the same proof here is the one I gave previously for the real case, for the symmetric case, where you show that lambda is real by showing that it's equal to its own conjugate. Now, the book's proof is not that hard to follow either, and it is important to note it as well. So in the book on page 187, recall this. We know that the inner product of AV with V is real. We had that in a previous video. All right. So if we look at AVV, which is, again, the inner product of lambda VV, let's take out the lambda times the inner product of VV, but VV must be real and positive. Hence, lambda is real. And so you see there that that proof is very quick and easy and simple to follow. Now, Theorem 5.2. This is a good characterization concerning eigenvectors for Hermitian operators. When A is a Hermitian operator and V is an eigenvector of A, okay? Now, if W is perpendicular to V, then AW is also perpendicular to V. All right? That's important. Now, when you have a single vector V and you look at it being a subspace of V, all right, and you have the orthogonal complement W perp, then you notice that your dimension theorem holds. I have a mistake here. Under span V, that should be 1 and not n, because it has to add up to be n. So excuse my typo. But we have the spectral theorem for the Hermitian case. When A is a Hermitian operator, then V always has an orthonormal basis of eigenvectors. Okay? Theorem 5.4 says when we look at the matrix case, when V is the matrices having complex entries, let A be Hermitian matrix. Remember, that means that the adjoint of A equals A. Remember, the adjoint of A is the conjugate transpose. That means that there exists a complex unitary matrix U so that U star AU, which now is equal to U inverse AU, equals the diagonal D, with the diagonal entries being the eigenvalues. Now, remember the unitary case, the inverse is equal to the adjoint. So U inverse equals U star. In 8.6, we look at unitary operators one more time in the context of eigenvalues and eigenvectors. This is on page 227 and 228. Let V be a vector space over the complex numbers with a positive definite Hermitian product. Let U be a unitary operator. Remember the definition of a unitary operator. It preserves the scalar product, and it also preserves the norm of the vectors. And remember this, a unitary operator maps a unit vector to a unit vector. Now, since scalar field K is equal to the complex numbers, we know already that U has an eigenvector with a non-zero eigenvalue. Why do we know that? Because U is invertible. All unitary matrices are invertible, okay? So the span of that one eigenvector, call it W, it's a subspace of V, is said to be stable under U or invariant under U. And then you look at the orthogonal complement, and we're not going to hold you responsible for that particular proof. But look at 8.6 theorem 6.2. Same hypotheses, V over C with a positive definite Hermitian product. U is a unitary operator. This is the important one I want to look at. V has an orthogonal basis of eigenvectors corresponding to U. That's important, and the proof is by induction. So you start out with a subspace of dimension 1, and then you look at the orthogonal complement. You expand it to a basis for the whole space, like we've done in the past, and using induction, you get an orthogonal basis for the whole entire space. The real case, you see then that if T is an operator that's real unitary, then the vector space can be decomposed into a direct sum of subspaces, invariant subspaces, V1, direct sum V2, dot, 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 direct sum V sub R, that are invariant subspaces that are mutually orthogonal to each other. That concludes our video.